This is Science Friday. I'm Ira Plato. After the Deepwater Horizon spill, BP poured nearly 2 million gallons of dispersants into the Gulf of Mexico. The goal, of course, is breaking up oil slicks, making them dissolve into ocean waters, sort of like how you squirt dish soap on a greasy frying pan to get the oil to wash away with the water. The problem is, after you dump all that soap into the Gulf, the soap stays there. My next guest has developed something that could be the solution, the soap that has iron in it, so that you can suck up the soap with a magnet. How did he do it, Bill? Could we really use something like this next time there's a big oil spill? Julian Eastoe is a professor in the School of Chemistry at the University of Bristol in the UK. Welcome to Science Friday.
Hello, Ira.
Hey.
From the United Kingdom.
Thanks for joining. How did you get this idea? It sounds so simple yet so easy.
Well, to explain that, I'd like to propose an interactive experiment for you and your listeners. Would that be okay?
Absolutely.
Well, the experiment works best if you're in the kitchen. So go over to the fridge and take one of those picture fridge magnets. You know, with Niagara Falls, Las Vegas, or Disneyland on it.
Right.
Then now go over to the kitchen sink with the magnet. Next, put the magnet against the bottle of dish soap. Right, what happens?
Nothing.
Absolutely nothing. That's because normal soap is not magnetic. Just as you said, you can't control where it goes. Gravity does that, just sucks it down the drain. Now, Ira, we've been making soaps and surfactants with unusual properties for some years. Have you ever thought of a soap you could turn on with the flick of a switch? A light-sensitive surfactant. We made one of those about 5 years ago. And next we thought, why not try magnets? Would it be possible to make surfactants or soaps that respond to magnets? Well, if that's true, then you stand a chance to control where the soap does and where it doesn't go. Our motivation for this was just good old-fashioned scientific inquisitiveness.
So you created the soap that is magnetic, so that the soap dissolves the grease, keeps the grease with it, and then you can just magnetize it away with a magnet.
Yeah, it sounds incredible, but it's true. I was witnessing the experiments in my laboratory at the University of Bristol this afternoon with graduate students. We were making emulsions with lube oil, our magnetic soap, and we were moving them around using magnets. The emulsions can be collected up.
And now I got an experiment for you. Tell me if this is possible. Let's say that you can disperse your magnetic soap into a harbor. Can you magnetize the hulls of ships so that they sort of scoot around the harbor, soaking up all the grease, collecting on their hulls, and then you just clean them off when they get back to the harbor?
Well, Ira, I haven't thought about that. It sounds feasible to me, but I think we would have to do some tests in the laboratory. I'm not sure about if you can maintain magnetism in the hull of a ship.
But do you think you can do this with an oil spill by collecting up all the grease later on?
Well, in principle, that's right. That's what we demonstrated in the laboratory. We started with chemicals that are relatives of common or garden soaps. We kept the organic part of the molecule, the one which dissolves oily substances. But we chemically modified the ionic part, which makes the compound water soluble. And it's quite simple, really. We replaced the normal ions with magnetic ions. Those ions contain the element iron.
And voila, because the soap molecule, as you say, is fascinating to begin with. One end likes to stick in the grease, and one end likes to stick in the water, and that's why it works so well. And you basically took the water end and put a piece of iron in there.
Yeah, we've done this with iron. That's in the paper which has been published recently, but we've even used other magnetic units. I can't disclose them right now because they're under a secrecy agreement. But we are now starting to optimize the chemistry, and that is now really exciting. I think what this research shows is the first stage in any scientific breakthrough, the essential proof of principle. And once the proof of principle has been established and has been communicated to the scientific community, that's when it gets really interesting.
Yeah.
That's when the collective consciousness, those thousands and thousands of scientific minds get to work coming up with ideas that you would never have thought of.
Yeah, I see. So once you show that this can happen, and people will say, this is what I can do. Sort of like...
Now, it was suggested to me, Ira, by somebody from the British equivalent of the Audubon Society. That's the Royal Society for the Protection of Birds in the United Kingdom. That this could potentially help in the cleanup of those poor seabirds when they get contaminated by oil slicks.
They get washed down with this magnetic soap.
Yeah, he suggested that maybe with the extra pull from the magnet, you would be able to clean off the poor birds more effectively than just using the traditional, dispersants. So I sent a grad student down to the store to get some lube oil and a pillow. We've taken it apart, and we're testing that idea right now with down from the pillows that we bought in the store.
I'm sure the grad students are doing it, right?
Sure.
Once these things happen, like you never know where they're going to end up. I mean, the laser beam was invented to cut steel and razor blades with back in the early 60s, but look what it's used for now. You never know where your idea might wind up, where it will end.
So that's the really exciting thing about being a scientist, is that you uncover facts and figures that you just do not know where that will lead for the human race. Think about the liquid crystals, which were developed in the UK in the 1970s. When they developed liquid crystals, they had no idea that it would be an integral part of mobile phones and smartphones, for example. But they certainly don't work without liquid crystals to allow you to interface with the electronics through the screen. And this is the same it could be here with this application, the applications that could come from this magnetic soap.
Now, let me ask you the $64 question, as we say here in the States. And it is a $64 question, I guess. Is it cheap enough?
Well, in fact, it's interesting that what we started with are chemicals that are just the brothers and sisters of those that you would find in household products. We try to keep it simple here. And the cost of our magnetic soap is already reasonable. It's reasonable enough that it could actually be scaled up. Think that the elements that are contained in this soap are carbon, hydrogen, nitrogen, chlorine, and iron. All very, very common elements. And therefore, the soap that we've made is cheap, commercially viable.
Well, I wish you the best of luck, and we'll watch to see where your soap shows up, so to speak.
Okay, thank you very much.
Thanks for taking time to be with us today. Julian Easto.
It's been a great pleasure, Ira.
You're quite welcome. Julian Easto is a professor in the School of Chemistry